Today, we're stepping into one of the toughest system design interviews you can face, and we're going to walk out with a strong hire. We're going to design a file synchronization service, like Google Drive or Dropbox, piece by piece. Let's break down the answer that lands you the job.
So imagine this. You're in the room, the whiteboard is totally clean, and this is the question they hit you with. On the surface, it sounds simple, right? Upload a file, see it everywhere. But believe me, the answer you give is what separates a rejection from an offer for a top-tier leadership role.
Because, see, this isn't just a coding problem. The interviewer wants to know if you can think about trade-offs, if you can see catastrophic failures before they happen, and if you can actually steer the product. They're not just looking for an engineer, they're looking for a leader. So let's show them one. Now, the first move a leader makes isn't drawing boxes and arrows on a whiteboard. It's asking why and for who. Before we even think about architecture, we have to define exactly what we're building, and maybe more importantly, what we're not building. A really strong answer always starts by scoping the problem. We're not trying to boil the ocean here. We're building a focused minimum viable product, an MVP. That means we have to absolutely nail the essentials. Smooth uploading and downloading, that automatic sync that feels like pure magic, file versioning because losing someone's data is a cardinal sin, and to start, just some simple read-only sharing.
And now, here's the move that signals you're a leader. You challenge the requirements. You ask the clarifying question that shows you're already thinking about the deep trade-offs. Okay, so are we building this for a designer syncing small files instantly where latency is key? Or are we building it for someone backing up their entire 1 terabyte hard drive where throughput is everything? For this design, we're going to state our assumption. We are all in on low latency sync for productivity.
Okay, so our scope is defined. Now we can finally head to the whiteboard. It's time to sketch out that 30,000-foot view of the system. Let's figure out how all the major pieces are going to fit together. The single most critical architectural decision we're going to make is split the system in two. On one side, we have the control plane. Think of this as the brain. It handles all the information about the files, the file name, its permissions, version history, all that stuff. Then, on the other side, you've got the data plane. This is the warehouse. It's just dumb storage. It doesn't know anything about your files. It just holds the raw bits and bytes. This separation, right here, is the key to building a system that can scale to millions of users. So the first piece of our puzzle is the app that's actually on your laptop or your phone. And it's not just some simple user interface. No, this client is smart. It's doing a ton of the heavy lifting. It's got a watcher that's constantly monitoring your files for any changes. The second it sees one, a chunker intelligently breaks that file into smaller pieces for a really efficient upload. And the whole time, an indexer is keeping a local database, which is how you can still work even when you're offline. And that brings us to the heart of our control plane, the metadata server. This thing is the absolute single source of truth for everything. If you rename a file, if you move a folder, if you share a link, this is the server that handles that transaction. It is the most critical part of our system, and it absolutely positively cannot make mistakes. That's why we need what's called strong consistency. It just means that when you rename a folder, that change happens instantly and everywhere, with no weird delays or conflicts. For a system like this, that's completely non-negotiable. All right, we've sketched the blueprint, but now comes the part of the interview where they really separate the good from the great. We have to pick a few really complex areas and go deep to prove we get the real-world engineering challenges. So let's dive right into the core sync engine. So the interviewer throws this classic, super practical problem at you. We've all been there, right? You're uploading a huge file, your Wi-Fi flickers for just a second, and boom, you have to start all over again. A naive design would create a terrible user experience. So, how do we solve this? The answer is so elegant. We don't upload files, we upload chunks. We take that 5 gigabyte file and we break it into hundreds of little 4 megabyte pieces. And this unlocks 3 huge benefits. First, resumability. If one chunk fails, we just retry that one tiny piece. Second, deduplication. If you and I both upload the exact same movie, the system is smart enough to only store one copy of those chunks. And third, and this is amazing, bandwidth savings. If you change just one sentence in a huge report, we only have to sync the one tiny chunk that actually changed. It's a game changer. So how do we make that sync feel so instantaneous? Well, just constantly asking the server, hey, anything new, is super wasteful. Instead, we use this really clever push system. When client A updates a file, the metadata server gets notified, and it pushes a little message into a queue. A notification service then sends a tiny pulse to client B. Now, this pulse travels through what's called a long polling connection, which is really just a connection the client keeps open, just waiting to hear something. That pulse tells the client, hey, wake up. And then it asks the server for the specific changes. It's incredibly efficient, and it's what makes the whole thing feel like magic. Okay, so we've built a solid system. The architecture is sound. But a true leader doesn't just build for the sunny day. They anticipate how the system will break under pressure. So now, the interviewer is going to start throwing curveballs, those tricky edge cases designed to test your ability to handle real-world chaos. Here's the first one. Our system is great for big video files. But what happens when a developer tries to sync something like their node_modules folder? Suddenly, we're hit with 100,000 tiny little files, and the whole system just freezes. What's the root cause here? The trap is to think about the total storage size. 100,000 tiny files might only be a few megabytes total. The real problem isn't the space, it's the operational overhead. Every single one of those files creates a new row in our metadata database and requires a completely separate API call. We're not being crushed by one big blow. We're dying from a million tiny paper cuts. So, the strong hire answer is to state a clear, decisive strategy. You say, we need to stop treating these small files as individuals. We have to bundle them. This approach is sometimes called a haystack model. It was famously used by Facebook for handling photos. And here's how it works. First, the client on the user's computer intelligently groups thousands of these little files into one single larger file that we'll just call a brick. Second, our metadata server now only has to track that one brick, but it also keeps this lightweight index that maps which small file lives at which byte position inside of it. And finally, when a user needs just one of those tiny files, the client does something called a byte range read. It's basically telling the storage server, hey, I don't need the whole brick, just give me the bytes from this position to that position. It efficiently plucks out the one small file it needs, and the problem is completely solved. Okay, next curveball. This one's a high-pressure scenario. A file has gone viral, it violates copyright, and the legal department is on the phone. They need it gone now, and it's already been shared with 1 million people. How do you pull the plug? Instantly. Well, the obvious answer is definitely the wrong one. If you try to run a command to delete 1 million rows from your database all at once, you would likely cause a massive database lock, potentially taking down the entire service for everybody. It's way too slow and way too dangerous. The elegant solution leverages the architecture we already have, specifically our deduplication system. Remember how every file chunk has a unique hash? The winning answer is this. We don't delete the data, we block access to it by tombstoning its hash. Here's the 3-step takedown. First, we add the file's unique content hash to a blazing fast cache, something like Redis, and we mark it as banned. Second, we modify our code so that every single download request first checks this banned list. If it finds a match, we immediately return an error, and access is blocked. Instantly. And finally, a slow, careful background job can run over the next few days to clean up all those database references without any emergency. By getting through those curveballs, you've proven your technical chops. The final step is to elevate the conversation one more time, to show that you're thinking about the business and the long-term health of the whole system, because it's really about making smart trade-offs. And this is where you really step into that leadership role, by framing technical choices in terms of business trade-offs. Take deduplication, for example. We could implement it just at the user level. That's pretty simple to do, low complexity, gives us medium savings. Or we could build a massive global system that finds duplicate files across all 100 million users. That would save a ton of money on storage, but the technical complexity and the risk are very, very high. A leader can explain this trade-off clearly and recommend starting with the safer option first. And that's really the core takeaway here. A winning system design isn't about finding the one correct technical answer. It's a performance. It shows you can scope a problem, you can architect a robust solution, you can anticipate how it's going to fail, and you can make intelligent trade-offs between cost, complexity, and features. You've proven you're not just an engineer, you're a leader. Congratulations, you got the job.